Okay, so now I defined my basis functions that way. Let's start to derive the linear form. So I'm going to represent my solution UH being a linear combination of I goes from 1 to n being the number of interior grid points of ui times phi. Okay, phi are the piecewise linear and continuous functions I was just visualizing. So what we need is the bilinear form on AH and V, and here I can substitute V by any of these basis functions. Vj has to be equal to L of Vj. If I have this satisfied, then I can make any linear combination, let's say, of these equalities and get the same equality for any V in the same linear space. Okay, so for J goes from 1 to n. So the left-hand side, I can use the bilinearity of U and expand this by pulling the summation and all the coefficients out. So it's going to be a summation over I ui times A of phi I and phi j is equal to L of phi j, right? So then our task is to evaluate this and call this Aij, and evaluate this and call this Bj. Then what I get is the matrix A times my solution U1 to Un is going to be equal to the vector B. That allows me to solve for the linear combination coefficients Ui, which turns out to be the height of these basis functions. Right? Questions so far? Okay, now let's figure out how to evaluate these Aij's. So Aij is equal to A of phi I, phi j, right? Which is equal to the integral over the domain of the gradient of phi I dot product with the gradient of phi j. Again, this is going to be a very sparse matrix, because let's just go back into MATLAB and visualize this one, and let's hold on. Let's make a V also equal to the zeros. Let's make a V into an arbitrary other. Let's say 100 is equal to 1. Let's do another trisurf of this with V. Okay. Right, so I get two basis functions. One is the blue one is the yellow one. So if I and j are equal to 100 and 200, what is Aij in that case? It's going to be 0, because if we look at the formula for Aij, it is the integral over the entire domain of the gradient of phi I times the gradient of phi j. And the gradient of phi I and phi j has no overlap in the areas where they are non-zero. Okay, so for example, the yellow one is only non-zero in 1, 2, 3, 4, 5 elements, 5 of these triangles. The blue one is less clear, maybe 6. Yeah, blue one I think is 6, but like each one is only going to be non-zero in the triangles that shares that particular point. Okay, so now it's a little bit more complex than the one-dimensional case. In one-dimensional case, and a basis function is only non-zero in 2 elements, right, left and right. In this case, each basis function is going to be non-zero in a small number of elements, but that small number is no longer going to be a constant. It depends on the yellow one has 5, the blue one has 6. Okay. So, but anyway, these are going to be equal to integration. It's going to be, let's split that up into summation of elements. So elements. So let's say k in the elements integration over omega k. So omega k is the kth triangle. Gradient phi, gradient phi j dx. This is good because over each element, both phi and phi j are linear. So the gradient of phi and gradient phi j, they are what? Constant, right? So then I can write this as summation of k in the elements, gradient of phi in that element dot with gradient of phi j in that element times the area of that element k. Okay, up to now all calculus is gone. Only thing left is geometry and algebra. All right.